Swayam Prabha. Digital India. Educated India.
Now, if you didn't have, so let's go from here into a problem 3. Now, if I have a phi which is not 1 to 1, suppose it's many to 1, phi is many to 1, then in that case, how can I still maintain an equivalence between 2 and star? So that is the question here. Is without, when it's not 1 to 1, how can I maintain the correspondence between 2 and star? So, if there are multiple z's, okay, that correspond to the same, that give you the same x, or for okay, if you are on the other or the basically the issue is that not for every x there need not be a z, right? For every x there need not be a z. In that case, what can one, how can we still ensure a correspondence between 2 and star? So, so the trick to do that is the following. See, the why did we fail here when we substitute, when there are multiple, there are x's for which there is no z. In that case, what can have, what kind of problem happens? We substituted phi of z as x and we got to problem star, right? We substituted phi of z as x and got problem star. And in that case, what has happened as a result? We are searching over too many x's, right? Far more many than we were supposed to in problem 2, right? So, what we can do is bring that back in through the constraints. Okay. So suppose I look at this problem. So, this has all the constraints that star has, and in addition to that, it is requiring that x must be equal to phi of z. So, let me write it like this: x minus phi of z is equal to 0. So, x should be such that there is a z for which x is equal to phi of z. Okay. And now I am minimizing over both variables x and z. So, as x varies, z will also vary, but my additional constraint here, x equal to phi of z, this ensures that I am searching only over those x's for which there is a corresponding z. This automatically constrains my problem star to search only over those x's for which there is a corresponding z, and this therefore becomes equivalent to problem 2. Is this clear? So, if I get from here, if I if I have a solution x hat here, suppose x hat solves 3 if and only if z, which is equal to phi of sorry, phi inverse of, not phi inverse, sorry, if and only if So, actually let us take x hat z hat, this thing solves 3. Okay. So, if x hat z hat this that solves 3, let me put it right like this, x hat comma z hat solves 3, then you must have that x hat is equal to phi of z hat, that is because of the constraint, and z hat solves 2, okay, and this is equivalent. Is this clear? So, you can bring it, do the substitution or change of variables, but then if you are losing if you are losing information by about the z by transforming it to star, you can bring it back through the back door by putting it as a constraint. Okay. Now, it may or may not simplify the problem, that depends on the problem at hand. Sometimes, for example, one of the one of the issues that occurs is you can have algorithms might not be able to process these kind of functions, function passed to another function. It may make errors in calculating gradients and so on. Those kind of issues can occur. So, it is much cleaner to then write out, give them one function, one clean function in each constraint, okay, and then put this as an additional constraint. The cost you pay for this is now you have additional variables also. So, your problem size has increased in terms of the number of variables you are optimizing over. So, this can sometimes be a cleaner way of formulating the problem than formulating in this sort of this kind of complicated manner. Okay. Yes. Yeah, so that could be another a case where you cannot for which a case where you have um, for for every x there need not be a z. That sort of case would be when you are changing dimension also. So, if you are mapping down, for example, so if you are going from Rn to something small, some Rk where k is smaller than n, in that case there will be vectors in the range space which are not for which there is no corresponding z. Right? Yeah. Okay. So, another commonly used trick, which is probably you already know, is to do transformations that are of a monotone kind, but I will explain this in a much more in a better way now, in a more general way. So, you may have seen, for example, when you want, instead of trying to maximize say the exponential of a certain function, one of the things that people do is instead just simply take logarithms on the same function, and then you maximize the log of it. And the reason for that is that log is a monotone function, right. So, that's the thing that I will now tell you in a much more general way. So, look at this. So, suppose here psi 0 is a monotone increasing function. Suppose also psi 1 till psi m, these are all functions from R to R, and they are such that they satisfy psi I of x less than equal to 0 if and only if not x, let me denote this by u, psi I of u less than equal to 0 if and only if u is less than equal to 0. Okay. And suppose psi m plus 1 till psi m plus p, these are also functions from R to R, and they satisfy psi I of u equal to 0 if and only if u equals 0. Now you define say f tilde as psi 0 composed with f and g tilde I as psi I composed with g I and h tilde j as psi m plus j composed with h j. So, I am composing this time from the left, all right. So, and now you look at this optimization problem, which is my problem 4. I am now minimizing f tilde of x. This transformation does not change my space, it is still x, subject to g tilde I of x less than equal to 0 for all I 1 to m, h tilde j of x equal to 0 for all j equals 1 to p. Okay. So, this is my optimization problem. Now, this is actually equivalent to star. So, how do you see again we want to say that these are equivalent. Equivalent in what sense? Equivalent means solving one gets you to the solution of the other, right. Now, in this case actually it is even better. So, first let us compare the feasible regions of the two. Can you say something about the feasible regions of the two? Feasible region of this problem, problem 4. How does that compare with the feasible region of star? So, suppose I have an x that is that is feasible for 4. Let us start with 4. Okay. I have a x that is feasible for 4, okay, which means it satisfies all these constraints, satisfies all the inequality constraints, all the equality constraints. Now, g I tilde of x is less than equal to 0. Now, let us take this as just as an example. Let us take a g I tilde of x less than equal to 0. Now, g I tilde is what was g I tilde? G I tilde was psi composed with g I, right. So, it says, so this is saying psi I of g I of x less than equal to 0. And if you see my condition on these psi i's for I from 1 to m, the condition is simply that psi I of u is less than equal to 0 if and only if u is less than equal to 0, right. So, if I look at all the x's, such that this is less than equal to 0, which is equal to the x's such that this is less than equal to 0, that is actually the same as the x's for which g I of x is less than equal to 0, because psi I of g I of x is less than equal to 0 if and only if g I of x is less than equal to 0. That follows from the underlined thing property here. And similarly, you can do this for all the inequality constraints together. Likewise, for the equality constraints, you have that psi I of u of is equal to 0 if and only if u is equal to 0. Okay. So, which means that u is the only 0 of this function psi. So, it can have whatever shape you want, but it has only one 0 which is at 0, right. So, in that case again what will happen is that x such that h tilde j of x equals 0 if this set the x's for which h tilde j of x is equal to 0 is the set for which h j of x is equal to 0, right. So, their feasible regions are, so the feasible region of the two problems are the same. Feasible region of 4 is equal to the feasible region of feasible region of star. What about the objective? The objective has been transformed through a monotone increasing function, right. So, if you have a solution x star of star, so you have that f of x star is less than equal to f of x for all x feasible, then it will also be that f tilde of x star is less than equal to f tilde of x for all x feasible. This is because on an inequality I can always apply a monotone increasing function, and that does not change the direction of the inequality, right. So, right. So, this is if and only if this is an increasing function. So, it is also invertible. So, I can go back and forth. So, what this would mean is that the optimal value of 4 is going to be psi 0 applied to the optimal psi 0 of the optimal value of star, right. So, the optimal value of 4 is optimal value of star with psi 0 outside. Let us look at another example of transforming problems, this time which concerns introducing additional variables and changing the nature of constraints. Okay. So, look at this problem. So, minimizing now f x subject to, I have my equality constraints h j of x equal to 0, the original equality constraints, but I will also do the following thing. I write gi of x, which was an inequality. Let me write it like this: gi of x plus si equal to 0. Okay. This is for all I 1 to m. Well, but this si is a new variable that I introduced. Now, remember gi of x, was less in the original problem was less than equal to 0. So, there is a gap between, so gi of x is and 0, there is a gap here. So, I can fit in a positive number here between gi of x and 0 and make the two such that this becomes equal, right. So, that is that number s. Okay. So, si is now something that is greater than equal to 0, that has been fitted into that gap. Now, as my x changes, okay, it's for in order to maintain this equation here. Okay. In order to maintain this equation, my s will change value. Okay. So, it is I need to bring that in also as a variable. That cannot, it is not a constant anymore. Okay. It has to be, if I make it a constant, then that will change the meaning of my constraint. Okay. It has to also float as my x changes. So, my variables now are x as well as s. So, so what has happened as a result of this transformation? What's happened is I have earlier I had inequalities on G. Okay, now I have an equality constraint in G, but I have introduced new variables which are these S's, and I have now an inequality on the S's, right. So, my earlier problem, if you look at star, it had m inequality constraints and p equality constraints, and of course, n variables. On the other hand, 5 has now m inequality constraints. How many equality constraints? m plus p equality constraints, and how many variables? M plus n variables. Now, what is the advantage of doing something like this? There is one there are sort of it has its one key advantage is that it standardizes things quite a bit for us. So, all equalities will now be of a very simple form, which is all inequality constraints can be without loss of generality considered to be of this very simple form. That means there are some variable greater than equal to 0, right. So you don't, so inequality constraints will simply take the form of defining some quadrant or some orthant in your space, and equality constraints will define surfaces in the space, right. Whereas earlier you had surfaces defined by equality constraints and you had regions defined by inequality constraints, and that interaction can be a little complicated. This tends to make things a lot simpler. Okay. So yes, yeah. So that is Si greater than equal to 0 is the inequality constraint. So the question is, what are the inequality constraints in problem 5? These are the inequality constraints. It's a variable. It's a the function Si itself is being asked to be greater than equal to 0, right? Yes. It should be treated as an independent variable. See, eventually all these variables will interact. You have to pick an optimal choice for all of them together. Jointly need to be chosen. Okay. But when we write variables in an optimization problem, if one is known to be a function of the other, right, then you should substitute and get rid of that. Right. So that is so you eventually you are left with this bunch of independent decisions that are bound by constraints. That is how one poses the problem. So Si is another variable, but then it's the values it can take is dictated by these two constraints. That so once you tell me the x, it fixes the range for Si for every I. Is this clear? And of course, in the optimal value, they have to all be chosen together. They cannot be chosen, independently of each other, because their regions are such that you need to know one to know what the other is. So as I was saying, so can you observe why the two are equivalent first? We have not I have not discussed that. So why is phi equivalent to star? So see, remember, so the way to observe this is if you look at the feasible region of star. You look at the feasible region of star, this is the x is such that all the constraints of star hold. Now, how do I compare this with the feasible region of phi, which is not in the same space anymore, because now it has more variables, right? Phi is both in the x and the s space, so it's in a larger dimensional space. So how do I compare the feasible region of star and the feasible region of phi? No. See, Si is not present in my original problem. In present in star. So how do I compare the feasible region of star with that of phi? Well, the one way to do this is to observe the following. See, the feasible region of star is the x such that the constraints of star hold. Okay. Now, the feasible region of phi can be brought in the following way. You look at the x such that together with s, Okay. So, what I have written here is this is, so look at the set of x's for which you can find some s, okay, such that x and s together satisfy the constraints of phi. So, x and s, if they together satisfy the constraints of phi, right, and you look at such x's, only the x component of that x comma s pair. Okay. Now, for those x's, wouldn't the constraints of star hold automatically, right? Because if x comma s satisfies the constraints of phi, what, of course, j of x would be equal to 0. All of these would be satisfied. J of x would be equal to 0, and here you would have that gi of x plus si equals 0, and si would be greater than equal to 0. Okay. But gi of x plus si equal to 0 and si greater than equal to 0 would mean that gi of x is less than equal to 0, right. So, these two together implicitly automatically imply that gi of x is less than equal to 0, right. So, consequently, what has happened is that the x's for which star the constraints of star are satisfied is the same as the x's for which you can find some s, such that the constraints of 5 are satisfied with x and s together. So, that basically ensures that these feasible regions, this is the sort of way you can establish a link between the two feasible regions. Geometrically, what is happening is, if you want a picture here, suppose here, here is the space, here is a region of on which you have defined the feasible region of star. This is the feasible region of star. What we have done here is sort of by introducing an additional variable, the feasible region of 5 has become something like this. So, feasible region of star here is this box, is this flat square here, whereas the feasible region of star is this red 3-dimensional box, and it is such that if I take the shadow of this box onto one of the variables, that we look at its projection onto one, that gives me back the feasible region of star. So, this is the region of x, this is the space of x's, the additional axis that we have, that is the space of s. So, any point x here has a corresponding s, such that x comma s together lie in this floating box on top. Okay, that is your x comma s. And likewise, if I take an x comma s here, I can project that back down to get to a point in the feasible region of star, right. So, the feasible region of star is in some sense a shadow of the feasible region of phi, right, shadow or projection, or however you want to think of it. Okay. So, now, but this simply relates the two feasible regions. Why are they equivalent, the optimization problems? So, the reason they are equivalent is because, see, in star you are optimizing only over this plane here, this sort of square, the region over the feasible region down here. Okay, but and in 5, in 5 the objective function has not changed going from star to phi. You have introduced this new variable s, but that variable does not appear in the objective. What matters for the objective is the value of x alone. It is still f of x which is the objective, which was the objective earlier also in star also. So, the f of x's that you can get, the values of f of x that you can get in star is the same as the values of f of x that you can get in phi, right. So, as a result, the the objective values will actually be the same. Okay. So, the bottom line is that if you have a solution x star is a solution of star, this implies that there exists a S star such that x star S star is a solution of phi. And likewise, if x star S star solves phi, then x star is a solution of star. Okay. So, this is how you can go back and forth, and in fact, moreover the optimal value of star would be equal to the optimal value of phi. So, this new variable s that we just introduced has a name, it is what is called a slack variable. Okay, so the s is what is called a slack variable, that is